My name is Attila Szegedi, and I mostly work with Marcus, so speak up? Okay. Okay, so hi, I'm Attila. I work with Marcus, so this presentation is sort of a logical extension of his morning presentation, although at some point I was actually just thinking of putting up one slide, basically what Marcus said. But the situation is actually not that bad. I will really try to take over from where he left. This is the Oracle Legal slide, and I usually always skip it or make a joke about it, but this time it's actually relevant because I will be talking about future directions, and it is actually relevant that I can tell you anything. It's pretty much, this slide is great. It's a free card. I can lie anything to you, and I still don't have any legal consequences. This is great. So, what I want to talk to you about is where do we want to take Nashorn in the future? And the general idea that we outline is getting to a point where we have a library, or rather a tool chain, really, for implementing dynamic language runtimes on the JVM. And the first question is, okay, so why are we doing this? Still a bit quiet? Yeah. All right. Do you guys in the back hear me okay? All right, okay. So anyway, so why are we doing this? It's aside from the usual reasoning of because it's there is another reasoning, which is most of the languages, well, all of the language implementations on the JVM will need to follow one of the two strategies, interpretation or compilation to bytecode. And we deal with the compilation to bytecode here. So you will have your source code, and you want it to run through any number of intermediate steps that will somehow materialize themselves. And we would like to take as much pain out of that for as many people as possible. We'll see how far can we get with that. Just as an illustration, reusing code, reusing Nashorn code would be a great thing because I did a quick check on the some open source project tracking websites. V8 has 972 significant lines of code, almost 1 million. Nashorn has a little bit more than 200,000, which is to be expected because Nashorn actually does rely on the JVM for a bunch of services. We don't have to write any of the I/O, any of the memory management, any of the object model. It's all there for us, right? Now, logical next step in my thinking was, okay, so let's take as much as we can from Nashorn's 200K lines and make it usable for you guys out there so that when you set out to implement a language runtime, maybe you will only need to write another 50K significant lines of code, and 150 or something can be reused from Nashorn. So again, might be a pie in the sky. I hope it's not, but we will see. So what are those things that Nashorn can do today and that would be really great for other things? And I always have to say that we are talking in terms of targeting JVM bytecode, targeting JVM as it exists by the JVM specification today, any JVM as a matter of fact. So I'm not just talking Oracle hotspot. I am typically thinking in terms of solutions that will work on any VM. Nashorn itself is such that it's part of the OpenJDK. If you have a different VM that is able to run with OpenJDK, with a Java 8 level JDK, it would run on it. There is no VM-specific smarts, no Oracle-specific APIs that it is dependent on. And with this work, I also want to keep ourselves in this land. So whatever we want to come up with is something that is completely compatible with a Java virtual machine and Java platform as it is today. So I'm saying this because number 3 on the list is splitting large methods and array initializer and object initializers as well. And well, today, JVM bytecode has this unfortunate limitation of 64K bytecode instructions per method. And there is plenty of examples of dynamic languages having programs with really humongous methods. And I am not saying whether that's a good thing or it's a bad thing. Quite often, these things can arise from using dynamic language, such as JavaScript, as a compiler target, really. So we still have Emscripten and Mandrill that basically take C source code and basically compile it using JavaScript as an assembly target. It's quite fascinating, but it tends to generate methods that are a little bit on the biggish side. So Nashorn these days, things that Markus has already demonstrated, we do specialized compilation based on the input types of the parameters of the functions, and we do it lazily. So basically, first time you invoke a function with specific parameter types is when we generate it. We have this whole thing with the gradual de-optimization with on-stack code replacement and continuations, which is a really long-winded way of saying something, so we just call it optimistic typing. Then I spent probably about 3 months at the beginning of this year, maybe a little bit more, writing a static type analyzer in a dynamic language. Sounds crazy, but it's really useful, as you will see. And, you know, assorted garden variety of compiler optimizations. And there's probably other things. So parameter type specialized compilation is, this is what it is. If you have a JavaScript function, really simple, takes 1 argument, square, then if you invoke this thing with an int, it will generate the bytecode that you see on the top of the right side, which will take an int argument, do the multiplication, the one that you saw in the morning with the mul instruction not being an imul, but rather an invoke dynamic that takes care of the overflows. And if you invoke it with a floating point, then at that point, another version of the function will be generated that takes a double, and in that case, it will just load it twice, multiply, return. So, and all of these different type compilations can be live at the same time in the JVM. They don't supersede or obsolete each other, or we just keep one of them. No, we will keep, well, after we generated it, it's linked into a call site, so as long as that call site has a reference to it, it will actually be alive, right? And of course, if you invoke the function with an object, because why not? It's JavaScript, you can throw anything at it, then it will indeed generate a version of the function that will take an object. Oh, you also see that the actual JVM type signature of these functions is always 1 more than the actual argument. The first object argument is the JavaScript this. But we are generating as statics because the this is not any specific Java type. It can be any object. So instead of using instance methods, we are just using a static methods with the first argument always being an object. That's basically the JavaScript this being passed there. And so in this case, you indeed need to introduce the slowest by convention kind of a 2-number conversion, so invoke the JS type to number twice. Obviously, the reason you need to invoke it twice is because you can construct your stateful object from hell that actually has a counter and it's JavaScript value off, which is what is implicitly invoked in JavaScript when you convert an object to a number, can just return, you know, subsequently larger numbers or a random number or whatever it wants. So you cannot just convert it to a number once and then just duplicate the top of the stack and multiply. I mean, haha, how naive, right? No, that's unfortunately not what you do. So another thing that we can do is arithmetic overflow is typically the other thing is, well, as things stand, sadly, sometimes you can square an int and the result does not fit in an int. It says like if an int and an int love each other very much, sometimes they make along. And this is a, yeah, let me actually go and demonstrate this. It's like, I actually don't have too many slides, so I decided to make up for it by dazzling you with some live coding. So, okay, so this one, actually, so Nason has this print code flag when you can see what did it actually generate. And it's also fairly easy to, oh, yeah, the function is named square. To find the function. So here you see this usual still visible, trying to get no line wraps. So this is the actual function, 7 bytecodes, and then you have this exception handler for the overflow that we saw. Now, if I go back and instead of 500, I say something larger, like 1 to the 17, shift should already work, then you can see that I will have my square that takes an int and returns an int, but sometimes later, I will actually generate another function when it's triggered by the exception. So this was all generated on the fly as the code was executing. That still takes an int, but this time it says, okay, well, I ran into a number once that could not be squared and fit into 32 bits, so it will just re-implement the operations on longs. And then, of course, there is the continuation as well, which in this case is actually a little bit uninteresting. The reason we have the NOP 8 rows is that our code generation strategy for the continuation is such that we just, in ASM, we just regenerate the function as it was originally, and then basically just as the first instruction, we have a go-to to the bottom where we do the whole take the rewrite exception, reconstruct local variables and the stack, put the return value back on stack, and then eventually jump into whatever would be the next instruction. And then we let ASM take care of filling in the dead code with NOP 8 rows. All right. So yeah, as you can see, the arithmetic overflow, the blue lines, we are guarding that section of the code with an unwarranted optimism exception. Larger functions can end up with many exception declarations, and then if the exception actually happens, then we just do the whole dance at the bottom where we create an array, populate it with the local variables, do an invoke dynamic to a populate array so that we don't actually have to keep around a bunch of differently shaped array populator code, and it's smaller in the bytecode, right? And then throw the thing. So if you go back, the imul with a math bootstrap method will actually link to this guy. And it's fairly mundane. What it does, it uses the Java-lang math multiply exact. Java 8 added add, subtract, multiply, divide, exact functions. Is there anything else? No, right? These are, Oh, negate exact, yes, that's right. Yeah, negate exact is funny because if you try to negate the integer min value, that will not be a 32-bit signed int. So it links to this guy, which just fast path, return math, multiply exact, which if inlined actually ends up being 2 assembly instructions. And if it catches the arithmetic exception, then we still have to perform the operation because we need to calculate the correct result, and we return that as part of the exception. So there is this convert the arguments to longs, multiply them, return back. The optimizing compilation also can happen on retrieving a property type. So in this small code snippet, the first optimistic version of the code that we generate will optimistically presume that a.foo is an int. And then we can crush its little optimistic hopes by passing in an object that has a foo property that actually is a double. So if you do that, you can again see what happens code-wise. This time it indeed is an F. So first time what we do is we emit this invoke dynamic, which is a signature is from my Dynalink stuff. It's important to learn to not worry and love long string constants because they're interned. So this basically says, get me in an order of preference, either a property or an array element or a method in case there are 3 different namespaces in JavaScript there aren't. And the reason we have the program point equals 2 here, it means that this is optimistic. So this int at the end, this is not coercible, right? I am not allowed, if this returns a double, to coerce it. Rather, at this point, I need to throw an exception. And then the rest is I multiply by 2, and I return. As you can see, we actually have 2 unwarranted optimism exception handlers because we can be overly optimistic with this guy, saying we won't get back a int, and we can be overly optimistic with this guy, saying that the multiplication with overflow. And of course, here we have the exception handler. No big deal. And if you look further, we will see that this actually did the optimize. Now, invoke dynamic specifies a double return value. And since it's actually fed into a multiplication, we no longer even have the program point here. This is no longer an optimistic operation. At this point, it's actually coercible. So if the value of the property foo is some further object that can be converted to a number or a string, horrible dict2, because those can also be converted to a number in JavaScript, at this point, we allow coercion. This is just being smart in the type inference engine, saying the argument is fed to a multiplication operator in JavaScript. If it were an object, we would be converting it to a number anyway. So, and at this point, the other argument is also a double, and the multiplication result will anyway be a double. So this function actually got rid of all optimism. So as you can see, de-optimizing one call site, actually, as a consequence, had it that another call site also didn't have to be optimistic anymore. So just by invalidating one of those program points, the other also got propagated to double the multiplication. Double multiplication can't overflow. So this function is now these 10 bytecodes. It doesn't have an optimistic exception, unwarranted optimism exception handler. It doesn't have to have one. This function is, as we would call it, completely de-optimized. You can probably breeze to these slides because this is exactly all that I just told you. Yay. All right, and then another example of this, just to see how these rest of methods work. In this case, the rest of method will, when we need to do the continuation, right? Why do I not have my terminal? Terminal, where are you? This is silly. Bring all to front. There you are. Here it is. As you can see, the continuation method actually has a very funny signature. It actually takes the rewrite exception, because the rewrite exception carries in it the wide-end return value and the value of all the local variable slots. So what we do is we at first jump to the handler. And in the handler, what we do is we take the array containing the values of the bytecode slots, we load them from the array, and we store them into local variables. So this unpacks the array back into local variables. Sometimes it will, And then at the bottom, we do a return of the return value, which needs to be on stack, convert it to a number here, because it might not be converted. There is an interesting corner case of exception handler. And jump back to this guy, which will then end up with the, yep? No, it's not. Question was, is the unwarranted optimism exception or rewrite exception subclass of unwarranted optimism exception? No, they are two completely independent ones. Unwarranted is always caught within the function that is optimistic, and it only carries the program point and the return value that could not fit into the original expected type. And the rewrite exception, in addition, also contains the values of the local variable slots and is thrown outside of the function and is actually handled by the linker. Who throws which one? The method that encounters unwarranted optimism exception will be throwing it. So here at the first version that has the unwarranted optimism exception handlers will, in its handler, basically all that the handler does is constructs everything that's then needed. This invoke static rewrite exception create is a factory method for rewrite exception. The only reason we are using invoke static is that it's less bytecodes than doing the whole new, dupe, whatever, pushing it down so that the pre-constructed arguments are lower and so on. You understand? So, okay, so what I was, right, so basically what I was explaining is that, and here you see how we are using it. Get return value destructive, it's a technicality. It's, we did actually have a test where we were testing the fact that some things are not holding on to references where they shouldn't. And just by having the rewrite exception still being on the stack and having a long-running rest of method, this test started failing. So get return value destructive. It returns the return value from the rewrite exception and nulls it out. That's why that's the reason for a funny name. Also, a small corner case that you don't necessarily think about until you have seen it. Also, we have an awesome test suite in Nashorn. And yeah, as I said, sometimes you don't want to be optimistic. So in JavaScript, like bitwise or 0 is your canonical way to express that what you want needs to be coerced into a 32-bit signed int, 32-bit int. And if you're doing this, then we would just use ordinary multiplication, because why bother with an optimism if you would coerce the value anyway afterwards? So going back to what else can Nashorn do, type inference. So at first it really sounds silly, right? It's like, why the hell are you doing statical type inference in a dynamic language? But the answer is obviously because we are targeting a static bytecode format. So the bytecode format has iload and imul and whatnot, so you need to. And if you don't want to have, as in Marcus' presentation, have everything being naive, you need to have proper local variable type analysis. Well, type analysis in general. So we are calculating types of expressions, calculating types of local variables. We are propagating them from defs to use sites, the usual stuff. It is currently operates on AST, as everything in Nashorn currently operates on AST. We'll get to that in a moment. Which has its limitations, but it's actually pretty good right now. And it also handles a bunch of tricky control flow situations, like transferring control into a catch block is a hell, because generally you cannot really know when it transfers. So basically, the chosen strategy is that every assignment has an implicit has basically an implicit control flow edge to the beginning of the catch exception, conservatively saying that, well, if it was assigned this type, you have to presume that it can be observed with that type in the catch. But we actually keep both types alive. So if you say start with an int and then promote it to a double, we will actually try to, in a try block, keep using it as a double, even though we filled out use it as an int, even though we filled out the double slot as well, proactively there, in case that you reach the catch block, because in catch block, it's only the double that can be live. And, there's also like break from a finally that contains a return statement that took a bit to get right. Handling undefined, this is also a wonderful thing, right? So in Java, you don't have to deal with this. But bytecode does not allow reading an uninitialized variable. And so when you compile to bytecode, you have to deal with JavaScript actually allowing you to read an uninitialized variable. Again, static analysis is great for that because the variable, until it's initialized, we just have a synthetic type undefined. And when you try to load something that has a type undefined, then we just do a constant load of undefined there. And yeah, that's pretty much it. So in this case, if you try to print the value of I, and then afterwards you use it, then it will not actually force it to be an object. So if you look into it, one of these undefineds is the this, and the other is actually the argument. So the load of I just gets promoted to a constant. And if you look at the bottom of the method, there is only one slot for I, which is the int slot. And that's the one that's being used subsequently from here. So we don't let artificial reads of undefined inflate the type of our variable. That's actually a very significant thing, especially with the loops, when sometimes you enter a loop and you just like first initialize something there that used to be quite obnoxious. And of course, we have variables in multiple types. Again, you saw this in Marco's slide. In this case, in this example, we will allocate 2 slots for I, one that is an int and another that's an object. And then on the join point on the exit of the if statement, we actually need to box I because it is object because it can be undefined, right? Now, in this case, we don't have a statically provable undefined. We have it's either undefined or it's an int. So unfortunately, the union of these 2 types currently is object. So there's not much you can do here. We actually introduce a kind of synthetic else block that will do an initialization to the undefined at that point. But we are trying to keep it in the optimal type as long as possible. There is an interesting another case of this, which is parameters with multiple types. So if your input parameter is reassigned and is reassigned to something wider than it came in as, that also requires you to have a bit of a prologue in your function. So if you invoke this function with an int, you will generate a version that takes an int and an int for x and a y, but then you assign x to something that will become a double, and suddenly you need another slot. Now, of course, if our variable type to slot mapping would have been awfully generic, we could have just allocate another temporary variable at the end of the temporary variable slots. But, well, for various reasons, we right now do it so that all the slots for one variable are continuous one after the other. This simplifies things, but it complicates things in this case when we need to start the function by making sure that we right-shift the parameters to make space for additional slots, and then the local variable table is already emitted like that. It doesn't cause any particular trouble because Hotspot is really good at dealing with these kinds of essentially renumberings. Yeah, we have a bunch of really nifty dead code elimination as well, but one of those was actually some bits and pieces of dead code elimination actually came out from eliminating unnecessary type assignments to types. So it sort of fell out of it. On AST, I did actually spend quite a lot of time trying to figure out an algorithm for variable liveness analysis on an AST. It was a good mind work while jogging or washing dishes or being in a shower. It probably took up my mental cycles for these tasks for 2 weeks solid. And I couldn't figure it out. And, you know, also there's, as they say, you know, that moment when you realize that your homework is not solvable by Googling, right? So there's no literature on it, so that was already a sign that, okay, so either I solve this and I'll be famous, or it can be solved. As it turns out, it can be solved. I mean, I couldn't solve it and couldn't find anybody that could have solved it before. Yeah, he sent me a paper. The paper was about imposing a CFG on top of an AST. Not the same thing. So, with that in mind, I was starting, and that was actually one of the points where I was really thinking that we need another intermediate language. And NASA's compiler pipeline these days, the way it looks like, is that we have the source code, and then we have a parser, and then we got an AST. And then the AST is being shoved through a bunch of transformations, like typical lowering, symbol assignments, code splitting, local variable type inference, optimistic type calculations, and you know, at the end of the whole thing, you have the code gen. And code gen takes AST and churns out JVM bytecode. And that thing is really heavy. It's probably 4,000 lines or so. It's really big, and it's hard to disentangle. And because it has to know how to emit code for optimistic operations, needs to deal with emitting code for continuation handling. When you have just an identifier in your AST, it is a completely different code emission sequence if it's a load or it's a store, or if it's a self-assignment, if it's an increment operation, right? Control flow handover for split functions and so on. That's all that needs to be handled on the code generation level. So this code gen arrow, it's meant to be a little thick. That guy is heavy. So that actually got me thinking is that, what about if we had a separate step for some kind of a bytecode linearization of the AST, which would be something in JavaScript that produces some linearized basic block and control flow kind of a representation, but it doesn't have types, because we still didn't calculate types. For types, liveness, and so on. And if we had that, then we could have another type calculations and optimizations that work more nicely on a control flow graph, right? And then just at the end, we have the code gen, which at that point is actually much lighter. So we could split, one nice way to split this big code gen that we have in NASFON right now is to split it into an AST to this typeless or dynamic bytecode, do a bunch of transformations on it, and then bang, have this, have another very straightforward linear bytecode format to linear bytecode format transformer. And this is where the reuse comes in, because that bytecode format at that point is no longer language dependent, well, or less language dependent, but it's good enough for us because, as I said, liveness analysis, that thing needs backwards control flow traversal, damn it. And even though if bytecode, I mean, Java bytecode is arguably Java language dependent, right? I mean, it has a new operator for constructing Java objects. But still, if we have an IR that's like fairly close to JVM bytecode, sans types and various other things, then that can be reasonably used by other language runtimes as well if they target this bytecode format, this intermediate bytecode. I'm not talking about a new class file format for the JVM. I'm not talking about this even having a definitive binary representation. This thing only needs to exist as an in-memory representation that's being passed through a pipeline, right? I mean, I don't want to go there. We don't need the binary format. This thing doesn't need to be written out to disk. I mean, if somebody wants to do it, it's okay, but that's not the goal. So the idea is really, I mean, whenever I need to do a 5-second elevator pitch for this thing, I just say, it's like LLVM, except for dynamic languages on the JVM. So how would that thing look like? So the idea is that if you have a simple function that just multiplies two things, then you can emit a type-specialized version of it that takes two ints and then doesn't necessarily, I mean, here parameters are known, but otherwise you would be inferring them. And you could emit something where you just say load I, load Y. Oh, load I. Should be X, sorry. Ugh. So load X, load Y, multiply return. It's very similar to JVM bytecode. It's then you pass this to my stuff, and we infer the types. And we figure out that, oh yeah, and we assign you the bytecode slot, so you could just keep being symbolic here. So you could say load X, and I would translate it to I load 1. So I figure out the I, and I figure out the 1. And then I figure out that the mul actually has to be invoked dynamic imul, and I figure out that in that case I need to add you the whole catch unwarranted optimism exception, yada yada. I mean, taken from this dynamic bytecode representation, we can do that thing. So you as a language implementer only need to produce the bottom left representation from your top left representation. So as I said, you can emit symbolic identifiers, we'll infer types for you, we'll figure out when optimistic operations need to be emitted, we can set up the exception handlers, we can give you the a method that will generate you the continuations. It's like that. It infers the return types for functions because they're always a function of the input parameter types and the actual code. For a property getter, right, so you could have, so a GetProp operation would be something that ends up being compiled to a Dynalinks property getter. It's pretty much an equivalent of getField, except it's not a getField, it's a getProp, and then it retrieves a property on your domain-specific object. Obviously, and again, don't forget, we are a little bit still in the pie-in-the-sky mode here, is I can imagine that some of these operations would actually need to be language definable, but that's no problem with that. If there are like basically templetable snippets, then we're fine. So you can have a chance to decide for yourself how exactly a GetProp does need to translate to a bytecode in your system if the defaults we provide are not sufficient. Oh yeah, the function type actually during regeneration can also evolve from int to long to double and so on. And these are also things that we can, in linking the call site, we actually know how to handle that. A lexical scope getter. No, this is a funny one because, again, most dynamic languages can get variables from lexical scope. JVM bytecode doesn't do that, right? It only deals with locals. So this is again something that I really hope that we can get to a point where we can actually let you just emit like getProp foo, and it figures out that, sorry, not getProp foo, no, getProp, oh, it's X. In this example, it's the X that comes in the scope because we have a function F and we have a function G, and in its lexical scope you have the parameter X. And this load X actually on the right-hand side, this is actually an ASRM code. What it does, the first argument is actually a script function object. Those come with a method getScope that you can retrieve a scope from them. And then you can load that and you can just get the, do a get property X on it. And this distinction of whether this is a local variable, something I need to retrieve from the scope, is again something that I believe that we can actually manage on the IR level, hopefully. We can for JavaScript. Again, you need to forgive me for now thinking in terms of JavaScript. That's pretty much what I basically live and sleep with for the past 2 years. So, but that's also why I want to present all of this to you so that we can have a discussion about what else is needed. Yeah, what I said. Oh, and of course, another thing with these scoped getters is that they can also be optimistic, right? So if you, in this example, if you would have been using the Y variable, then the getter for that could actually be optimistic, and the inner function can be independently regenerated of the outer function, recompiled if it needs to be. And then it's really just at the end of the pipeline, we have the thing that takes a dynamic bytecode and translates it in a JVM bytecode after it actually received this type annotation. So like a load X would become iLoad 3 or dateload 5 or whatever. And the load of a variable can also become a scoped getter. A multiplication can actually be translated to an actual imul or dmul, or maybe an invoke dynamic thing. Getting a property on an object would also translate to an invoke dynamic something. This is how it actually builds on current invoke dynamic stuff. And of course, there is the mundane things that I don't really want to talk about a lot, like splitting the large methods into less than 64K JVM bytecode chunks. I don't like talking about that because it's annoying, right? It's a limit that's just there in the class file format, and you need to dance around that. And of course, no solution to it is actually perfect because you always need to weigh things across where do you split the chunks. If you're fortunate, your language has statements. If you're not, then they're just huge expressions. And figuring out just how to split it. An optimal split is an NP-complete problem because when you split it into multiple bytecode methods, they cannot share local variables. So if you have variables that are used by more of them, you need to force it into an artificial lexical scope object. Bah. But split functions are also subject to the optimizing recompilation. That's actually something that is not yet complete in Nashorn. We have a patch set, but it requires a bit of work to be completed. And then there are things that you don't even think about. It's like when you're doing the optimistic operation, sometimes you need to, sometimes you have stuff on stack, right? So consider this guy. You do the first squaring of x, and then you have it on stack, and you want to do the squaring of y, and then it throws an unwarranted optimism exception because of an overflow. And now you actually need to, when you do the continuation, you need to restore that squared x on top of the stack somehow. But, I mean, how? When you throw an exception in the JVM, the stack gets erased. So what we do is, in our bytecode emitter, when we reach something like that, then as you can see on the blue on the left-hand side, we have an iStore3, iLoad3. Basically, after we did the multiplication of x, we just stash it into a temporary local variable, reload it from there, and then if the exception triggers, then we can actually retrieve that value from the temporary local variable. So at some points, we actually need to selectively introduce this kind of synthetic store loads into a temporary variable. Otherwise you would lose significant values on the stack that you need to restore in your continuation. This is, of course, it could be improved because right now we also have a situation, like consider this guy, where g is invoked with the value of x squared, and then you pass x, and then you pass y squared. And so what we do is we load there's the multiplication result, and then we load x, and then we get, oh, I now have an optimistic operation again, and then in order to actually get back to that x square that I now need to store, I actually have to like pop that x from the stack, store the square, and push it back. This is actually a deficiency of our current code generation ASM, basically, that we already generated code for loading the next argument before we know that the previous argument actually needs to be stashed. So we need to adjust post facto. A better approach would be that. And again, if we actually have an IR-based representation instead of our stack-based representation, we could do that. So this is again a point where an IR-based representation wins. Yeah, it's great. I'm narrating all of my slides in advance. And of course, we could also be avoiding all these things by figuring out if a value on the stack is actually completely reproducible from constants or current local values. And then in the continuation, we could just perform those computations again instead of saving the value and restoring the value. That's a trade-off. But these are all strategies that can be tried once you have the intermediate representation. And of course, there's this linking aspect of just how do you link a call site so that when a method that you invoke through it comes back with a rewrite exception, then you divert execution into the compiler, compile two new versions of the code, one the optimized and one continuation, and then you run the continuation. And funnily enough, you have to link it in such a manner that the continuation itself can also de-optimize, because those things actually like cascadingly can de-optimize until they once execute completely. We try to, when we embarked on this, we actually first had a version where the continuation. We generated one continuation which is completely de-optimized, just totally pessimistic. Said, for like one-off execution, it will be fine. It turned out it's not fine, because if it operates or any variables in its external scope or in globals, it will actually pollute it with wider types if it itself is pessimistic. Because sometimes then it will do all the multiplications as doubles, and it will produce a double 3.0 and stash it into a global variable, and that global variable, damn it, now hosts a double, and it could be an int. So that's why we actually generate also still optimistic. The continuations themselves are generated as optimistic, so they can cascadingly slowly de-optimize. And don't get me started on the optimization of mutually recursive functions when you actually have another version of it on the stack. We handle that too. So, yeah. No. What? We solved all those problems so that you don't have to. Yeah. So summary. And I don't actually have no idea how we're dealing with time, but this is my last slide. Is that cool? So yeah. So there were a lot of hard things in this. I have to say this was probably one of the most interesting periods of my professional life, actually working on this thing. And I mean, spent 3 months writing a static analyzer for dynamic language. We did this all crazy, how do we do on-stack code replacement purely in bytecode without resorting to JVM tricks. Last year, Marcus and I attended Java 1, but aside from giving our talks, we were pretty much holed up in the speakers' lounge and just coding, which is also what we did on our flight over here. And it was great, but it was a lot of hard stuff, and we would like to offer those as a reusable library. And of course, this reusable library will need some input format to work on, and for that, we will need to figure out this almost bytecode with optional types, because ASTs are too high level and language specific. And this is also why I was actually really happy to hear that that JRuby 9000, right? JRuby 9000 is also moving toward this kind of an IR representation. And it just dawned on me when Charlie was giving his presentation that this IR format is also good for something else. It can be interpreted. So we might even defer compilation if that's something that we find useful. So yeah, that's the general direction that we would like to potentially move forward, but it still requires a lot of discussion, and this is really just something that we are setting our sights on. But it all works in Nashorn, but it's not reusable. So, okay, I think I did this twice. All right, well, thank you very much.